Is this what the future holds in store? Drowned cities, flooded lowlands, disappearing islands. A lot of people think so. Carbon dioxide from power stations and cars, methane from cattle and from rice paddies, burning of tropical rainforest. All are implicated in the so-called greenhouse effect, widely predicted to cause global sea level to rise at rates unprecedented in human history. It all sounds most alarming. So let's try and put it in perspective. Mean sea level defined here at Newlyn in Cornwall provides the ordnance datum for the whole of Britain. If you've used any ordnance survey maps made since about 1920, the contour lines on those maps are drawn with reference to mean sea level right here. This building is the Newlyn Tidal Observatory, and the reference point for ordnance datum is inside. And here it is, the observatory benchmark. The top of this brass bolt is exactly 4.7512 meters, that's 15.588 feet, above the mean sea level that was defined here at Newlyn back in 1921. Well now, how is mean sea level defined? That's where tidal observatories come in. This is the tidal gauge. And from it, from the gauge, this wire leads down into this well to a float on the surface of the water. And the float goes up and down with the tides, because at the bottom of the well, below low tide level, there's a pipe leading out to sea. The point is to damp down the effect of the waves. And that's why this is called a stilling well. Now from the float, the wire leads back up and over this pulley, which drives the pen recorder on the tidal gauge. And it's nice to know that in this high-tech era, machines like this can still be useful. Brass cogs and gear wheels drive the pen recorder, and as the drum rotates, the pen traces out a continuous, permanent record of the tides. It's accurate to about 1 centimetre or 2, which is pretty good, considering that the tidal range can be several meters. If you want to predict the tides for any particular location, you need a good set of tidal records over a long period of time. And you also need to know how the relative positions of the Earth and the Sun and the Moon change with time. The gravitational pull of the Moon causes the sea to bulge towards it. The Sun has a similar effect. When the Moon and the Sun act together, the tidal range is at its maximum, the spring tides. 2 weeks later, at half moon, the Moon and the Sun act at right angles to each other, and the tidal range is at its minimum, the neap tides. But predicting tidal motions is not as easy as it seems. The Proudman Oceanographic Laboratory at Bidston, near Liverpool, is Britain's principal research centre for the study of tides and global sea level. Just inside the entrance is this magnificent tide predicting machine. It was used from 1949 to the early 1960s for the compilation of tide tables for most of Britain's ports. It's a mechanical computer, the last of a line that began with Lord Kelvin's tide predicting machine in the mid-19th century. The phases and amplitudes of 42 different tidal components appropriate to a particular location are obtained from long-period tidal records and from astronomical data. These wheels represent 2 of the main tidal components. M2 is the principal lunar component, which is semi-diurnal. S2 is one of the solar components. A chart record can also be made. It takes a day and a half to prepare the annual tide tables for a single port. This marvelous piece of precision engineering has been superseded by the electronic computer, and that can handle over 100 tidal components, and it takes only a few minutes to prepare a set of annual tide tables. Tidal cycles are so regular that tides can be calculated for centuries ahead or for centuries past. Bidston scientists are always being asked by historians to tell them the state of the tide when some important event occurred. And looking ahead, what time will high tide be at Newlyn, for instance, in the year 2050 on March the 16th? The first high tide on that day will be at 09:19 and the height will be 4.5 meters. Or will it? The level of the water in this stilling well at any one time doesn't depend only on tide-producing forces. The level is also affected by atmospheric conditions. The actual level recorded on the chart may well be different from the predicted level. In this tidal record, you can see immediately the fortnightly cycle of spring and neap tides. On closer inspection, you see two curves. The black one is the observed rise and fall of the tides, and the red curve is what was predicted would happen. There are some significant differences. On these 2 or 3 days, for instance, observed tides were about half a metre higher than predicted. These differences are called residuals. They're caused by changing weather conditions. So atmospheric variability can cause sea level to be higher or lower than predicted from astronomical data alone. If the level is lower than predicted, that can be inconvenient for ships trying to enter port. If the level is higher than predicted, then things like this can happen. In February 1953, East Anglia experienced catastrophic flooding. The sea flooded more than 1,000 square kilometres of land in Lincolnshire, in East Anglia, and up the Thames estuary. It was necessary to evacuate several thousand families, and the damage ran into tens of millions, even at 1953 prices. 3 factors combined to cause that disaster. One was low atmospheric pressure, which by itself raised the sea surface by nearly half a metre as this deep depression travelled south over the North Sea. The second factor was a strong northerly wind. Because of the Coriolis force, the net transport of water was onshore, which had the effect of piling up the water and making sea level along the coast even higher. The third, and perhaps the most important factor, was the high spring tide. Here's the tidal record for that part of early 1953. The red curve shows the predicted sea level for that night in February 1953, and the black curve shows the recorded level. The difference is the extra due to the storm surge. One outcome of the 1953 disaster was that work began on design and construction of the Thames barrier. Another outcome of the 1953 floods was that a storm tide warning service was set up at the British Met Office at Bracknell to enable more notice to be given of storm surge conditions. Nowadays, meteorological data can be combined with tidal data to predict what the water level is likely to be at key locations a short time ahead, and to compare predicted with actual water levels. Computer simulations of past storm surges can also help to predict when flooding is likely in future. The pink and brown area sweeping down the east coast represents a storm surge in February 1989. Water levels were a couple of meters above normal. But there were no floods because the storm surge coincided with neap tides. Britain has a permanent network of more than 30 tidal stations. They routinely send data automatically back to Bidston so that the predictions can be checked. Newlyn is special because it provides the national sea level datum. Since Ordnance Survey datum was established at Newlyn in 1921, the mean sea level here has risen by between 10 and 12 centimetres. Now, is that because the sea's come up or because the land's gone down? That's not such a daft question as it sounds. This step-like or terrace-like pattern is characteristic of raised beaches, clear evidence that the land must have risen relative to the sea. These raised beaches are in a tectonically active region, the Caribbean. If you try to measure sea level changes in tectonically active regions like the Caribbean, you can expect a lot of variability. So if you want to monitor global sea level with coastal tide gauges, you need to use data from sites like Newlyn, where you can be fairly confident that they're geologically stable. Sea level has been continuously monitored by coastal tide gauges in many parts of the world for well over 100 years in some places. The record at Brest on the Brittany Peninsula goes back to before the Battle of Waterloo. The record's very noisy. The weather's never the same 2 years in a row, so the mean annual value can vary by several centimeters from year to year. All the same, the overall trend is upwards, just like it is at Newlyn. And at Cascais in Portugal, at Esbjerg in Denmark, at San Francisco, at Bombay and at Sydney, all the trends are upwards. That's the pattern of most records around the world. They all tell us that global sea level is going up by 1 to 2 millimeters a year. What's the reason for this progressive rise of sea level? Well, here's the principal reason. The world only began to recover from the last ice age around 15,000 years ago. As the glaciers melted and the ice caps shrank, more and more water was released back into the oceans, and sea level rose. Of course, it's only glaciers and ice caps melting on land that can cause sea level to rise. Floating ice, like icebergs and pack ice, already in the sea, can't affect sea level when it melts. But melting of ice on land isn't the only cause of rising sea level. Another important factor is thermal expansion of the water itself, as the whole ocean has warmed up since the last ice age. So this present-day rise of sea level could be simply a continuation of a process that began when the last ice age ended. But lots of people will tell you that the trend is going to accelerate, and the reason isn't far to seek. Everyone's heard of the greenhouse effect. Carbon dioxide and other gases, such as methane and chlorofluorocarbons, allow shortwave solar radiation to reach the Earth's surface. But they trap some of the returning long-wave radiation in the atmosphere. This atmospheric greenhouse enables Earth to support life, but human activities are interfering with it. Each year we burn more and more coal and oil and gas. We destroy more and more forests. That releases more and more carbon dioxide into the atmosphere. As its concentration in the atmosphere increases, so the world's climate is likely to get warmer, and sea level will rise more rapidly. But not all the carbon dioxide released by human activities stays in the atmosphere. About half goes into the oceans. Oceanographers need to find out more about the rate at which that happens. Aboard the research vessel Squilla, off Plymouth, Mike Whitfield.
We're all familiar with the effect of wind on wave, but there are some far more subtle processes taking place in the surface of the ocean that are going to affect our climate over the next few decades. Carbon dioxide is being drawn from the atmosphere into the oceans, and at the surface of the oceans, physical and biological processes are responsible for its flux into the deep water. The biological processes are related to photosynthesis in the surface layers. The physical processes are related to the stirring of the ocean surface and the transport of the water into the deep ocean. And the biogeochemical ocean flux study, what we're trying to do is to understand the dynamics of this process, to look at the biology and the fluxes of carbon associated with each stage in the biological process, looking at the air-sea exchange process, looking at carbon dioxide going through the ocean's surface, looking at the primary production, the conversion of the carbon dioxide into particulate carbon, looking at the grazing of the phytoplankton in the surface layers, the production of particles, and the way these particles sink into the deep ocean.
Sediment traps are used to measure the flux of particulate matter sinking from the surface of the oceans. Basically, the sediment trap is just a large funnel inside a cylinder, rather like a rain gauge. The particulate matter is collected in bottles, which are automatically rotated into position at preset intervals. Sediment trap studies are important because they can tell us about the way particulate matter breaks down and the rate at which it accumulates in sediments. And that, in turn, helps us to interpret the relationships between past climates and carbon dioxide levels in the atmosphere. But sediment traps can only give information about what's going on at particular locations.
Because the carbon dioxide problem is a global problem, we have to take a global perspective in the measurements that we make. Our satellites are ideal for this because they give us a broad, sweep picture of the distribution of productivity over the ocean surface. But the satellite only sees a few centimeters into the ocean surface, and we need to be able to take measurements within the oceans to relate the satellite pictures to the processes that we're investigating in the deep water. To do this, we developed a whole range of new techniques, including the undulating oceanographic recorder, to take light measurements which we can relate directly to satellite imagery.
This is the undulating oceanographic recorder, which is designed to measure the optical properties and the biogenic constituents of the water column while being towed by ships of opportunity, that's merchant ships or research ships, while on normal passage. It measures the optical properties with these sensors measuring downwelling light and upwelling light. The ratio of those gives the reflectance, which is proportional to the water leaving radiance as seen by the satellite in the various color bands. At the same time, we measure chlorophyll concentration with this sensor. Chlorophyll is the green pigment in plants that gives the ocean its color, and these data are recorded in situ using this solid-state data logger.
This is the NERC Satellite Image Processing Laboratory based in Plymouth. Black represents land and clouds. The white areas on the processed image represent the sea surface reflectance due to high concentrations of coccolithophores. They are phytoplankton which secrete external plates of calcium carbonate. The plates are shed by the organisms during growth and scattered when they die, and they reflect light strongly. This is an area of ocean between Rockall and Iceland taken in summer. When we look closer, you can see areas of high reflectance due to coccolithophores on the left to the west of a complex frontal system. Images like these can be calibrated using sea truth data on reflectance and biological productivity, obtained by towing instruments like the undulating oceanographic recorder through the area at the same time as the satellite image is recorded. Calibration is especially useful where the distribution of productivity is complex, for instance along fronts and in eddy systems. Understanding more about the flux of carbon dioxide into the deep oceans is important for making predictions about future climate changes and their effects on sea level. But direct monitoring of actual sea level change is also crucial. Tide gauges are installed at coastal sites and on islands all over the world. This one is on Truk in the Caroline Islands in the Pacific, complete with pen recorder and stilling well. There's a fair coverage on Hawaii and other islands in the Western Pacific. But in the southern Atlantic Ocean there are very few stations, and the same applies to the southern Indian Ocean. So what's to be done where there's no land on which tidal gauges can be sighted? One answer is to use deep-sea gauges called bottom pressure recorders that can be placed anywhere on the deep ocean floor. They are so sensitive they can measure a sea level change of only 1 centimeter in 6 kilometers of water. But it would be prohibitively expensive to provide enough of these instruments for a truly global coverage. So, is there another way? The only way to get a truly global measure of sea level change is from satellites. Orbiting at heights of 1,000 kilometers, satellite radar altimeters can measure sea level to 2 centimeters or better. Global sea level is rising by between 1 and 2 millimeters each year. The question is, will that rise accelerate because of our interference in the global greenhouse? People in low-lying regions like Bangladesh need to know. If sea level rise accelerates, scenes like this could become all too common. Professor P.K. Das is a former head of the Indian Meteorological Service. he has modelled storm surges in the Bay of Bengal.
If you were looking at the coastline, it would appear to be concave in shape. So if there is piling up of water as a consequence of the storm, that piling up would be much greater than it would be for a straight coastline. The second feature is the shallowness of the sea. It is much easier for the wind, you see, to lift a given volume of water if the depth is small. A meter rise is important because it can convert a containable tide into one that is not containable.
Many other places would also be affected. Islands and atolls like the Maldives and Tuvalu groups in the Indian and Pacific Oceans are little more than a meter or two above sea level now. An accelerating rise could be disastrous. The Thames Barrier was built to cope with storm surges. As sea level rises, it will need to be closed more often. So what does the future hold? If sea level at Newlyn goes on rising at its present rate, it will be 15 to 20 centimetres higher by the end of the next century. But what if the rise accelerates? This is just one model of what might happen. Sea level could be something like a metre higher by the end of the next century. But the record is so noisy that any effect won't show up until after the turn of the century. But to put all this into a planetary perspective, we need to look at it on a longer time scale. We get heat from the sun, and we know the Earth is continually altering its position relative to the sun. So the amount of solar radiation received by the Earth must also vary. For example, the angle of tilt of the Earth's axis varies, and this alters the latitudes of the tropics and polar circles. It takes 40,000 years to change the maximum tilt to minimum tilt and back again. At the same time, the axis wobbles like a top. It wobbles rather slowly and takes 21,000 years to go the full circle. This motion is called the precession of the equinoxes. The biggest change of all is caused by changes in the Earth's orbit round the sun. At present, it's almost circular, but it's very slowly becoming more elliptical. This change of orbit to elliptical and back to circular occurs about every 100,000 years, though it's not a completely regular change. These three periodic changes, the Milankovitch cycles, along with cyclical changes in the activity of the sun itself, lead to climatic variations which affect the amount of water frozen into glaciers and ice caps, as well as the mean temperature of seawater. And all that must have a considerable effect on sea level. A global rise of mean sea level of even half a metre or so could have serious consequences for some human societies. But actually, a rise of half a metre is pretty trivial from a planetary perspective. During the last 2 million years, for example, during the Pleistocene, sea level was going up and down by 100 meters or more at intervals of a few tens of thousands of years. And if you go further back into the Cretaceous, about 90 million years ago, sea level then was a couple of 100 meters higher at least than it is now, quite enough to drown everything around here. It makes you think, doesn't it?